Our last session before your finals. Okay. Okay. Yeah, hold on one second. Okay, go ahead. Okay. What part of this function is going to affect the domain the most? Why? It's because you can't take square roots of negative numbers. So, what does that mean? We can set x minus 2. What does that have to be? Does it have to be less than 0, greater than 0, greater than or equal to 0? Greater than or equal to 0. Or equal. X minus 2 can be equal to 0. You can take the square root of 0. Okay? So now we solve that inequality, and we get x has to be greater than or equal to 2. So there's your domain right there. Now, do you use interval notation or not? In other words, is this a sufficient answer, or do you need to put it in interval notation? Okay, so the domain, what would be the interval notation here? Do you know what interval notation is? Okay, it would be like this, 2 to infinity. Okay? In other words, that says the same thing as this, except for one exception. We always use parentheses next to infinities, but what goes next to the 2 depends on whether it's greater than or greater than and equal. If it can be equal to 2, then we need a bracket. And in this case, it's perfectly fine that it can be equal to 2. We can take the square root of 0. So 2 is an allowable number. 1.9? No. But 2 or above, notice that if it's 3, it's a positive number. If it's anything higher than 2, it's a positive number. So, sorry for the dogs barking. There's lots of thunder out. And that's what she does when it's thundering. Yeah. So the domain is relatively easy. We don't have to consider the -5 even. Only restriction on the domain is that radical sign. Okay? The range is something different. The range is actually quite a bit harder to solve. You have to do a little bit of out-of-the-box thinking. What's the lowest value that y can have? Okay, first of all, this, hold on, let me change colors. This can be 0. And I don't mean what's inside the radical sign, I mean the whole thing. In other words, the square root of x minus 2 can be 0. If x is 2, it's 0, right? Will that ever be negative, what I just circled? No, it never. The square root of a number is always positive. There's no such thing as a negative answer for the square root of any number. Okay? So the lowest value that can be is 0. So what is the lowest value on my range? No, 0 minus 5. Negative 5. And it can be negative 5. What's the highest value on my range? Infinity. In other words, if as x gets bigger and bigger and bigger, then the range just gets bigger and bigger and bigger. And if x approaches infinity, then the square root of infinity approaches infinity. And infinity minus 5 is infinity. Okay? In other words, the square root function looks like this. Starts there and it goes up. Always up, always up, always up. So if you go all the way to infinity on that axis, you're going to go all the way to infinity on that axis. It doesn't stop at some number. Okay? Hold on a second. Let me close this door. Pi, stay in here. Pi, come here. Stop barking. Yeah, that'll happen. Now, what I've graphed in blue is just the square root of x. Okay? We've got a couple of transformations going on here. It starts 2 units to the right, and it's shifted down by 5 units. So the actual function that we're looking at looks more like this. But notice it still goes from minus 5 on the bottom to infinity on the top. And that's what the range means. The range means what are all of the possible y values. Domain is all about x. Range is all about y. Range much harder to figure out than domain. Domain is pretty simple. There's very few functions that I can't tell you the domain in 10 seconds. Range, different story. All right, what else do we got? Okay. Base. Log base 4. What's the argument? H is the base. What's the argument? Like that? T? Okay. Now, first of all these log rules that you've learned only work if the base is the same. You can't have log base 3 and log base 4 and log base 5. Cannot combine them if that's the case. Okay? So when they say log base h, it means as long as h and h and h are the same bases, I can do all my log rules. So what's the first step in compression? It's kind of the last step in expansion. Compression is doing the reverse. Compression is you're going to take these 3 log statements and you're going to turn it into 1 log statement down here. And what goes in the argument is the question. Okay? And it's a multi-step procedure. When you are compressing, the first thing you want to do is get rid of these leading coefficients. What can I do with that 4? No. When you have a leading coefficient, you make it the exponent. So that 4 goes right there. What can I do with this 3? Same thing. Now, here's what I got. I got log base h of r to the 4th plus log base h of s minus log base h of t to the 3rd. Now use your sum and difference properties to put that all into one expression. In other words, the very next step is the one I have listed. We just have to fill in the argument. What is the argument going to be? I'll give you a hint. It's a fraction. What's in the numerator? No, I've already got the log in front. The only thing I'm looking for is the argument. In the numerator is that times that, and in the denominator is that. In other words, when you have logs that are being added or subtracted, you can turn it into a single log statement where the argument is being multiplied and divided. That statement going from there to there is true. And that's probably one of the most important properties of logs, is the fact that if you have 2 logs being added, you can turn it into 1 log of the 2 arguments being multiplied. So, let me test you. Tell me what the log of 2 plus the log of 3 equals. What are you going to do to those 2 arguments? You're not going to add them. You never do the same thing. If the logs are being added, then you got to multiply the arguments. Multiply the arguments. That's what it is. Get it? Okay, let me test you again with another one. The log of 4 minus the log of 2. And I don't write a base intentionally. In other words, this is log base 10, but it doesn't matter what the base is, as long as it's the same. As long as the base is the same in the 2 log expressions, you can always put it into 1 log expression, which is what? You don't multiply them now. we're doing subtraction. So, exactly. In other words, we're going to divide it. 4 over 2. And then you can simplify that into just 2. So the log of 4 minus the log of 2 is indeed equal to the log of 2. Okay? So that's what these are all about. And that's really the only other rule you need to know is this one here. If I have the log of 5 squared, and I want to expand that, what do I do? No, what you got to remember is that exponent. What can you do with that exponent? You can bring it down in front, always. And if it's down in front, you can take it back to be an exponent. So what is this thing equal to? That's it. And that's all the rules you need to know. You need to know what to do when you have an exponent, and you need to know what to do when you have separate log statements that are being added or subtracted. So, give me more problems from your end. Hold on, start again. Plus what? Okay, now the order you do these is important. Okay, you always do them in the reverse order. When you're compressing, you do them in the reverse order than when you're expanding. And we're going to compress in this case. How do you know? Because we got 3 log statements. If we had 1 log statement, it would be an expansion problem. Since we have multiple log expressions, it's going to be a compression problem. What's the first thing you do when you compress? Tell me what to write. Tell me what the next line should read. The base isn't to the 6th. Remember, there's a difference. There's a base, and there's an argument, and there's a leading coefficient. It's the argument to the 6th. 2 to the 6th. So all you're doing is doing that. You're taking that leading coefficient and making it the exponent of the argument. That's what you're always allowed to do. So what's the next part of it? Okay. And the last part of it, we don't need to do anything. There's no leading coefficient. So we've done step 1. Now we have to kind of combine all 3 of these. So in one step, tell me what the new argument is. No? Okay. No, hold on. Yes, it is a fraction, but only because we have a plus and a minus. So, in other words, that is multiplying the arguments. That is dividing the arguments. So what goes in my new argument? that times that. That's all. It's real simple. So what goes in the numerator? No, let's just write it like this. 2 to the 6 times 9 to the 1/2. That's all you're doing. What goes in the denominator? 3. The log that's being subtracted. So anything that's being added is multiplied. The arguments are multiplied. And anything that's being subtracted goes in the denominator. It's as simple as that. Okay? There's really only 3 rules that you have to follow. And that's the coefficient becomes the exponent of the argument. And anything being added gets multiplied, and anything being subtracted gets divided. Now, we can simplify this a little bit, and we should, because we're looking at all these numbers that we know what they are. What's 2 to the 6th? That's 64. I'll help you out on that one. Okay? What's 9 to the 1/2? Well, you need to know what the 1/2, very good. In other words, that means the square root of 9, right? That's what 9 to the 1/2 means, is the square root of 9. Well, I already had a 3 in the denominator, so now those 3's can cancel. And my final answer is something relatively simple. Log base h of 64. So these 3 log expressions turn into a very simple single log expression. So all you have to do is follow those 3 rules every time. If you're compressing, the first thing you do is bring the exponent up, and then you take anything that's being added and you multiply the arguments, and you take anything that's being subtracted and you divide that argument. It's that straightforward. Okay, so what else? You got another? Be nice if you have another compression, because I'd like to make sure you know how to do this. How much? 25? Notice I didn't write the h, because it doesn't matter. It can be log base anything. The whole reason they're putting in h is to tell you that it could be log base 10, it could be natural log, it could be log base 7, it could be log base anything. So I'm just going to leave the h out to avoid having to write much. So there's 2 log expressions there. We're going to condense them into one. What goes in the argument? Yep, which is 20. In other words, yeah, when you get 500 divided by 25, you want to simplify that because you can. In other words, I know that 500 divided by 25 is 20. So the simplest expression is log of 20. And I'll add the h just to make it prettier. All right, what else you got? Okay, let's do an expanded. Let's do that. That's just the reverse of what we've been doing. So what do you got? Like that? Is that the argument? Okay. Now, when we were condensing, the first thing we did was move the exponents. That's the last thing we're going to do when we're expanding. The first thing we're going to do is separate this into 3 log expressions. Okay? What's the first log expression? What's the second log expression? And what am I going to, and the fact that I'm expanding it means I got to put a plus or a minus here. What goes next? Yeah, because multiplication is happening. So it's log of q to the minus 3. And then finally, I got to take care of that r. So what am I going to do? Add or subtract? Yeah, hold on a second. I didn't quite write this correctly. It is a separate log expression. Okay, now we're not fully done yet. Got to do the last step. Got to take, as long as we're expanding, we need to get those exponents down in front as coefficients. So what's the next part? Yes, you do, Brandon. I know you know it. You're going to bring those coefficients down in front. Excuse me, you're going to bring those exponents down in front. Yes, no, that's exactly what it is. That's your answer. That's fully expanded. Fully expanded is when you have all the exponents down in front as coefficients. Okay? Now, this might look strange to you because if I were to condense that, I would end up with the q in the denominator. But notice that's where it belongs. I actually could have started this problem by moving that q into the denominator to begin with. In other words, I would have had p to the 4th there, q to the positive 3 times r. Those are the same expressions right there on the top. So all I did was move the q to the minus 3 to the other side of the fraction line. And now, if I were to expand that, I would get exactly what we got. I would get 4 log p, and then everything else is a divisor, so it's going to be subtracted. So we end up with the same answer that we got, doing it a slightly different way. What else? Natural log. Now, here's what ln, let me help you here. Here's what ln is. It's the log base e, which means the log base e is approximately 2.71. Nothing wrong with having a fractional base, okay? And e is one of those special numbers like pi. It's probably the second most important number in all of math. That's saying something, okay? So that's all, and that's why there's a special notation for log base e. It is so common when you go to higher maths like calculus, everything is natural log. Everything is log base e. So they give it its own expression, natural log. Okay, so that's what natural log means. Now, what did you have? Natural log of what? Okay, let's chop it apart, one step at a time. What's the first step? Hold on. We're just going to do one step at a time. Okay? What's the next term? It's plus or minus. Remember that when you are expanding an argument that has nothing but multiplication and division going on, you're expanding it into separate log expressions that are always being added or subtracted. That's it. In other words, multiplication and division turns into addition and subtraction. So the next thing has to be a minus, because the next thing is the denominator, which is being divided. So what's the next term? Sorry, what? No, we're taking one log expression, we're going to turn it into three log expressions. You got to put the ln first. That s is not being taken to the sixth, it's only the t. So it's ln of s. No, I realize that the denominators are multiplying, but the thing you care about is whether it's in the denominator or the numerator. If it's in the denominator, it's always minus. If it's in the numerator, it's always plus. Both the s and the t are in the denominator, so they're definitely both going to be minus. Now, what's the last step? Okay, tell me, read the line for me. That's how you do it. Every time. You turn anything in the numerator being multiplied into pluses, and you turn anything in the denominator into minuses. Believe it or not, at one time, this had enormous practicality. When I went to college, they didn't have calculators. You had to buy a slide rule. And the entire concept of a slide rule is based on this property of logs. If you multiply two things, if I want to know what the log of 2 times 3 is, that's the log of 2 plus the log of 3. Well, I got a little slide rule that tells me what the log of 2 plus the log of 3 is. And what that allows me to do is multiply 2 times 3. So you can multiply any two numbers with a slide rule and divide any two numbers. It's like the abacus of calculators. But it's all based on logs. All right, what else? Okay? No, they don't. I doubt that they want you to use your calculator. What's the first one? I can tell you real quickly. You're kidding me, really? You want to know what that is? Okay. The first thing you do when you have a log expression that you're trying to evaluate is, first of all, let's start with an easy one. I don't care what they're going to give you. I'm going to start with one that you can understand. Not you, one that anybody can understand. If I have the log base 9 of 27 and I want to know what that is, I start by putting a variable over here. It's equal to x. Excuse me, let me change that to that. Okay, if I want to know what the log base 9 of 81 is, first thing I'm going to do is call it x. And now I'm going to convert that to an exponential expression instead of a log expression. Every log expression can be converted to exponential, and every exponential can be converted to a log. In this case, it makes the most sense to convert it to an exponential. How do you do that? What's the next exponential expression I should write? No, the way I remember it is it's the number on the far left raised to the power of the number on the right equals the number in the middle. So you got 9 to the x equals 81. What's x? Okay, x is equal to 2. So now I can say that the log base 9 of 81 equals 2. That's a true statement. Why? Because 9 squared equals 81. So now let's go back to your problem. You had log base 9, and what was that big number? Well, I'm going to let that equal to x. Now I got 9 to the x equals 6,561. Do you have a calculator? There's only one way to solve that if x is an integer. And that's start taking powers of 9. In other words, you know it's not 9 squared. Try 9 cubed. If that doesn't give you that number, try 9 to the 4th. I bet you that gives it to you. So x equals 4. Why they would give you such a silly number like that, I don't know. Doesn't teach you a thing. Much better if I use 81. So let me give you one. What's log base 9 of 9 equal to? Very good, very good. I'm going to let it equal to x, and then I'm going to say 9 to the x has to equal 9. X has to be 1. And what that tells you is that whenever the base is equal to the argument, your answer is always 1. In other words, the log base 17 of 17 is also equal to 1. And that's useful. Remember that. The log base b of b is equal to 1, always, no matter what b is. Now, let's say they ask you to evaluate this on your calculator. You know how to do it? In other words, I can't do this the other way. If I do this, I have no idea what x is. X is not an integer. It's not 0, it's not 1, it's not 2. It's some fraction between 0 and 1. But what it is, I have no way of figuring that out. So in order to solve that log problem, I can't just convert it to exponential because it's not a whole number. That usually does not work. So there's something called the change of base formula. Okay? When you have, because you have a calculator that only has two keys on it. It has log base 10 and it has natural log, correct? So if they ask you the log base 9 of 8, you can't get that on your calculator. You can, but you have to use the change of base formula. The change of base formula says that it's equal to the log of the upper number, 8, divided by the log of the base number, 9. And you can get that on your calculator. So whenever you have a log that is not base 10 or is not natural log, you can always figure it out using the change of base formula. And the change of base formula goes like this. It's the log of A divided by the log of B. Notice it is not the log of A divided by B. It's the log of A divided by the log of B. Very important distinction. Because after all, the log of A divided by B would be the log of A minus the log of B. If I was expanding that. All right, what else you got? Okay. First of all, let me ask you something. Do you know how to solve a system of two variables and two equations? Okay, keep going. Well, the best way to do it is usually elimination. But there's no point in trying to do three variables unless you know how to do two. Okay, so what's the second one? Go ahead. Okay. Okay, let me label that equation 1, that equation 2, and that equation 3. Okay, now when you have three equations and three variables, you know you can solve it. The way you do it is you got to eliminate a variable. What variable? Here, these actually are easier to understand if you have all three variables and all three equations, but the goal is to take two of the equations and eliminate one variable, and then take any other two and eliminate the same variable. Okay? So, right off the get-go, I can tell that z is already gone from equation 3. So if I can eliminate z from equations 1 and 2, then z will be gone. And I will have two new equations that are just in x and y. And as long as I have two equations in x and y, I can solve it. So I have to turn this 3 equations and 3 unknowns into 2 equations and 2 unknowns. And like I said, it's actually a little easier to understand when you have all 3 variables in each one. But it doesn't matter, we can still do it. I can see that z is already gone from equation 3. So let's see if we can eliminate z by working with equation 1 and 2. What am I going to do? How do I eliminate z? It's not going to eliminate it. If I add negative z to 7z, I get 6z. By what? So tell me what to write. Instead of this being equation 1, I'm going to replace it with the blue equation 1. $98. Okay. Now let's just cross out that one because that's no longer equation 1. We've got equation 1. Now what do I have to do to eliminate z? Add them. Hold on. You're only going to do 2 things to a system of equations. You're either going to add them together or you're going to subtract them. That's the only things you can do. And since my goal is to eliminate z, I got to add them. If that was a plus 7z, I could subtract them. But it's not. It's a minus 7z in equation 1, and it's a plus 7z in equation 2. So that is going to create an equation 4, which is what? Add the x's. No, hold on. No, hold on. You're adding the blue 1 with the red 2. 35x. We're not adding it to 3. We're adding it to 2. 2 doesn't have an x in it. So if I add 35x to 0x, I get 35x. How many y's do you have? You got no z's, they go away, but you got to add the numbers. Okay. So that is part of our system of equations now. Okay? And notice that 3 already had z missing. So now I'm down to 2 equations and 2 variables. So let's solve this. In other words, I know for sure that I can solve for x and y. And once I solve for x and y, I'll be able to go back and solve for z. Because I got this equation here that just says 2y plus 7z equals 27. Well, once I solve for y, I'll be able to solve that for z easily. Now, I have 2 equations here. Not that easy to solve, or not that easy to eliminate a variable. What do I have to do? Nah, don't even think about substitution when you're looking at a system of equations that are both in standard format. By standard format, I mean the x's and the y's are on the left, the numbers on the right. When you have standard format, elimination is always going to be better than substitution. The key is how do I eliminate? What am I going to eliminate? How would I eliminate x? That would be tough. Y, not so tough. Well, how can I eliminate y? Very good. What's my new equation 3 going to be? What am I going to multiply the top equation 3 by? Okay, what am I going to multiply equation 4 by? Okay, perfect. So, equation 3, you said multiply it by 3, right? With me? Equation 4, you said multiply by -2. Now, how can I eliminate a variable? What do you do with, yeah, you get rid of it how? That's what I'm asking. You don't subtract. If I add +2 to -2, it goes to 0, right? So if one of these is plus and the other number is the same number but minus, you got to add them to get rid of it. If that was a plus 18y in equation 4, then I could still get rid of the y's, but I would have to subtract the two equations. So you do whatever you have to do. The reason you multiplied by -2 was that so you could do addition. Addition's always easier than subtraction. So if you can set these equations up so that you can add them in order to eliminate a variable, you're better off. Okay? So we're going to put a big red add sign right there. I'm adding everything. What do I get? I'm going to write it in the upper right-hand corner. What's x equal to? Really? They didn't make this? It's 214 divided by 82. I know, I hate it that they do that, but they do it. I can't do anything about it, so. Yeah, I don't know what other choice we have, so what is it? Okay, so we solved for x. Now, how do we solve for y? In other words, we got to work backwards now. We solved for one variable. That will, if we find an equation that only has two variables in it, and one of them is x, we can solve for y. What's the simplest equation that has y and x in it? The red 3. That one right there. Okay. You know, I don't want to do the math here. That's arithmetic. I'm not charging you $32 an hour to do arithmetic. That's why it upsets me when they give you these problems that have decimal answers like that. That doesn't do anybody any good. It doesn't help your understanding of it. It just makes us waste more time. But please tell me that you can solve for y given any value of x. Okay, so next you're going to solve for y. Let's make up a number. Y is equal to 4. Now, how do you solve for z? Because you got to solve for all three variables. Yeah, you could go back to this equation if you want. But there's actually a simpler one. That one right there doesn't need the x, just needs the y. If you have a value for y, you'll be able to solve for z. So you always do the simplest thing you can do. And it's simpler to plug in our y value into the red 2 equation than it is to plug in both x and y into the red 1 equation. So we're doing the easiest thing. We're going to use this equation right here. Put 4 in, you got 8 plus 7z equals 27. That means 7z equals 19. That means z equals 19 divided by 7. Okay? All right. Those are good problems. The problem is that they take about 15 minutes to solve. So you're never going to have more than one of them on a test. I can guarantee you that. Because they're not going to want you to spend 30 minutes on that. There's too many other things they want to test you on. So I'm not saying that it's not worthwhile to learn how to do it, but if you have to ignore anything, ignore that one. And I hate to say that. I don't really mean ignore it. But let's not spend the whole hour on 3 equations and 3 unknowns. If you can do 2 equations and 2 unknowns, you'll be fine. All right, we got just a few minutes. You got one last problem, and then I actually have a 7:30 appointment that I have. So that's it. All right. Well, Brandon, enjoyed working with you this semester, and I hope it's helped. And good luck on your final. And what are you going to be taking next year? Okay. I'll be around. I love both of those. Have a good one. I'll talk to you probably next semester. Bye-bye.